Let's get started. I'm excited. So, probability is the percent likelihood of an event or multiple events to happen. So, probability, once again, is just the likelihood of an event to happen. You know, how likely is this to happen? How likely is that to happen? Does everybody get what probability is? Okay, so probability is going to be written as a fraction or percent because it's either 0% likely to happen or 100%. If it's 0% likely, then it's not going to happen, correct? If I said to you, for example, what's the probability that there's a college student in this class? Well, 0 of us are, correct? So we would say 0% likelihood because there's none. Does that make sense, everybody? Not likely at all. If I was to pick any random person in this class, that they would be a college student. You got to interact with me. Does that make sense? I got to know if it's making sense. Okay. Now, if I said to you, what's the probability that I pick a student in this class who is a Westlake student? Wouldn't that be 100% likely? You're all Westlake students, so it'd be 100%. It's going to happen no matter what I choose. So think about it, guys. If it's written as a percent, that's pretty easy. It's from 0 to 100%. Now you're going to see it written as fractions. So like 1 out of 10. Oops. So you could see probability written as a fraction. So everybody, do you have a calculator available? If we had a probability, like for example, if I said to you, how many students in this class are my TA? Well, 1 back there, right? 1 out of how many students? 1, 2, 3, 4, 5, correct? So how many students total is there? 6 students, correct? So if I said to you, what's the likelihood of, if I choose one of you guys that you're going to be my TA? There's only 1 out of 6. So that would be written as a fraction. Does that make sense? So everybody type in your calculator 1 divided by 6. That would be the percent likelihood. So I want you all to do that right now. Type into a calculator. Any calculator will work. 1 divided by 6. 0.166, right? So that's, I'll show you 0.166. Everybody, let me show you how we would convert that to percent. So 6, and then there was 6 repeating. So doesn't it, let's just round to whole percent. So if I move the decimal 2 places, then that would be considered 16.6%, which is basically 17%. So you move the decimal 2 places. So that would be 17% likelihood of happening. Does that make sense? So this would be written as a fraction, and then this is that fraction as a percent. So you just literally type the fraction into your calculator. Okay. So I just told you, I'm going to write this down, how probability is formed. I just gave you an example. To find a probability of an event to occur, you'll take the actual outcome. So there was 1 student, actually, that was my TA, out of the total possible outcomes, out of you total possible. There's 6 of you possible. There's only 1 out of 6. Does everybody see? So write that down. Probability is found by taking the actual outcomes divided by possible outcomes, the total possible outcomes. So maybe I should add the word in there, total. Okay, so now if I asked you, what is the probability of flipping a quarter and landing on heads? How many total possibilities are there of flipping a quarter? How many outcomes? There's either heads or tails. So how many possible outcomes? 2, correct? That easy, it's really straightforward. So there's 2. So what's the possibility of if we flip the coin once that it lands on heads? 1 out of 2. Does everybody understand? Actually, there it is, actually happening, 1 divided by the total possible. So that's how probability works. So as a fraction, it's a half, and as a decimal, and then if you did that in your calculator, you get 0.50. So that would be 50% likelihood of occurring. So I really like probability. It's really straightforward for the most part. And we will get into more complicated stuff, but it's pretty like you just think about it. Okay, so another thing is independent events. Now this should just make sense, but if you need to take a little bit of notes, you could. Independent events are events that have no effect on the other happening. So for example, if we're looking at the probability of independent events, the probability of one happening will have no effect on the other. So if I flip a coin twice, for example, would the first flip change any probability on my second flip? No, right? When it flips, and then it won't affect my next flip, it's going to have nothing to do with my first flip, correct? So do you see how that doesn't change anything? So that would be considered an independent event. And we'll get into some dependent events later, but independent means one probability will not affect the other one happening. So here's an example of probability of an independent event. If here's a hat, we have 2 blue marbles, a red marble, and 3 green marbles. If we pull something out of the hat and then put it back in, aren't we starting back at the original place? So that would be considered if we have 2 events. If I pull something out, that's the first event. And if I put it back in and then pull something out again, the first event had no effect on the second event. Does everybody understand? However, let me show you something. Let's say that we pulled out, this would be considered dependent. So let me say to you, let me ask you a question here. What's the probability that I would draw a blue marble out of this hat? How many possible blue marbles are there? 2, correct, everybody? So there's 2 right now in there out of how many total? 1, 2, 3, 4, 5, 6 marbles. Does everybody understand? Okay, so now I pull out, let's pretend I don't replace it. So I pull out a blue marble, let's pretend. I'm going to cross out a blue marble. Now on my next one, because I'm not putting that blue marble back in, now my probability is going to change. How many total are there now? 5. So if I said to you, what's the probability of drawing a blue marble and then drawing a blue marble if you don't replace it? Now it's become dependent because now we don't have that blue marble in there. So we're looking at a new hat. Does that make sense? So do you see how the first event is now affecting my second event? Okay, so that would be okay though. Now what's the probability of drawing a blue marble given that this happened already? So now what's the probability of drawing a blue marble? 1 out of 5. So let's see which one was more likely to occur. Drawing blue marble the first time or drawing it the second time? Everybody type into your calculator. 2 divided by 6, give me a percent. Quickly. 33%, perfect. And what was the probability of the second time? 1 out of 5, what's that? Is it 2.2? So that's 20%. So do you see how interesting it is? It did affect the next probability. Does that make sense? It wasn't the same anymore, and anyway. So, and we won't get into, we're going to be dealing with independent events, so me replacing and putting that back in. Anyways, just kind of getting you understanding when a probability would affect it versus when it wouldn't. Okay, so once again, if we would have replaced the marble, it just would have been 2, 6 again, right? So that would be independent events. Okay, what is the probability of drawing a blue marble on the first draw? It's not a trick question. 3 out of 8. Does everybody understand why? Okay, awesome. And what's the probability of drawing a green marble? Okay, I'm just making sure we're understanding probability. Everybody good with that? Okay. Okay, so there's different ways to model probability. One is a tree diagram, which shows the possible outcomes we could get. And so we're going to learn how to do that. So instead of looking at actual probabilities, what I'm going to have you do is we're going to look at independent events. Now I'm doing 2 different things or doing something twice. We're going to list out the possible outcomes. We get a blue, then green. We get a heads, then a heads. We're going to list out all possible outcomes. So this is called a tree diagram, and it's just a tool to help you write out all the possible ways of an answers coming out. So everybody, it says, what are the possible outcomes of flipping a coin 3 times? So this is how I think through it. Okay, I'm going to hand out some. So if we flip a coin 3 times, the first event is the first flip. So maybe write this down. I would be taking notes right now. So our first event is the first flip. Now, we know they're independent because the first flip will not affect my second flip's probability, and that will not affect my third flip's probability. So what we're going to do right now is list out the possible answers we could get if we flip a coin, or possible outcomes. So if I flip a coin 1 time in the air, it's going to give me a heads or a tails, right? So we could get a heads or a tails on the first flip. Is everybody good with that? Now let's go on to that's the only possibilities. Let's go on to our second event. It's flipping the coin again. So flipping a coin again. We're flipping 1 coin again. Now we're going to make a tree diagram. So if I flip a coin, won't I get heads or tails, no matter what? So let's think about it. We're making a tree diagram showing the possible ways we could flip a coin the second time. So let's pretend like we flipped it once. We get a heads or a tails. Let's pretend we landed on heads. Everybody good? Now we're moving on. We're flipping our coin again. What are our possible outcomes? Heads or tails? So after we get a heads on our second flip, we could get a heads or a tails. Does everybody understand that piece? Now let's go back to our first event. Let's pretend on the first event we got a tails. Now let's flip our coin the second time. Weren't we going to get a heads or a tails? So after we got tails, the second time we got then a heads or a tails. So here are the possible outcomes after flipping two coins. Heads and getting a heads and a tails. Or we could have got a tails and a heads or a tails and a tails. Correct, everybody? Does everybody see how this is working? Nobody's confused. Okay, let's go on to our third flip. Our third flip, we could get either a heads or a tails. Same thing as the first and second flip. So let's focus in on, and I'm going to erase this just to give myself some room here. We got to branch this out. So we're on to our third flip. Now this is what you've got to think of it as. So let's pretend on our first flip we got a heads, and then our second flip we got a heads. Now we're to our third flip. Does everybody understand? On our third flip, we're going to get a heads or tails. So does everybody see how this tree branch is just going now? Let's pretend on our first flip we got a heads, on our second flip we got a tails. Now we're flipping the coin for the third time. We're going to get a heads or tails. Let's go back to, we're saying what if. What if we would have got a tails the first time and a heads the second time? Now we flip our coin the third time. We're going to get a heads or tails. And now we're going back to our first flip and saying, what if we would have got a tails the first flip, a tails the second flip, now we're flipping it the third time, we're going to get a heads or tails. So now what you can do is use this tree diagram to list out all possible outcomes. Everybody watch. So now let's go off to the side. We could have got heads, heads, heads. You see how now I can list out my outcomes very easily. We could have got a heads, 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 correct? We could have got a heads, heads, tails. Everybody good? We could have got a heads, tails, heads. We could have got a heads, tails, tails. So we're just listing out possible outcomes for our coin flip of 3. Let's pretend we would have got tails first. We could have got tails, heads, heads. Tails, heads, heads. We could have got tails, then heads, then tails. We could have got tails, then heads. I'm going to draw a line in between these. I kind of have them kind of going together on accident. And then we could have got a tails, tails, tails. Now what a tree diagram does is if you try to do that in your head, you would miss things. Like, you know what I mean? If you just sat and thought about, okay, what are all the possibilities? You're going to miss something or double dip on something. Does everybody see? And then not only this, it shows us the order in which we got the answers. These are the possible outcomes, correct? We listed all of them. Does everybody see? So now when dealing with probability, the question is, how many total possible outcomes? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 total possible outcomes. Okay, what I want you to do now is, if I said to you, what's the possibility that you got tails, tails, tails? How many times did that happen? 1 out of 8. So that would be our probability. So what I want you to do is I want you to flip the coin 3 times. And I want you to do this 3 different times. Record what you get, heads, tails, heads, or tails, tails, tails. And I want you to put what the probability of actually getting that was. Does that make sense, everybody? So you're all going to have different answers. You all have a quarter, flip it, write down I got a heads. Flip it, write down I got a tails. Flip it, I got down this. What's that probability? Just curious, did anybody get tails, tails, tails? Just curious. Yeah, it's kind of interesting. How many of you got, so my question is, how many of you got 2 heads in your answer? 1, 2, 3 of you. Okay, so let's see. I'm going to make a point here. I'm going to erase this. So I'm just going to erase this because now we have our possible outcomes. So if I said to you, how many of you got 2 heads? You said 3 of you did, which is quite a few of you, most of you, a lot of you. And how many of you got 2 tails? 1 of you, so 2 tails, 1 of you, and then, so then what was yours? Heads, 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 very interesting, okay, heads, heads, heads. So actually, if I said how many of you got at least 2 heads, 4 of you would have, right? Does everybody see? So let's look at this, let's think about this. Now let's change the probability question. Not what's the probability you got your sequence of events, but let's change the probability and I'm going to ask this. What is the probability that you'll get at least 2 heads? Raise right here, 2 heads, at least. How about right here? Yep. And how about right here? Yep. At least 2 heads. Oh, right there. And then that's it. So 1, 2, 3, 4 out of 8 chance, correct? So that's a 50% chance that you were to get 2 heads, at least 2 heads. Does everybody see it? So it's making sense because a lot of you did get that. So it's kind of making sense here. Then at least 2 tails. What's the probability of getting at least 2 tails? Isn't it 1, 2, 3, 4? Did I miss anything? 4 out of 8, which is 50%. That makes sense. Perfect. So as you can see, probability is making sense here. Good. Okay. So now, what was the probability of flipping 3 heads? How many times did that happen? Once out of 8. Correct, everybody? Wasn't that only 1 time out of 8? Okay, now I want you to do, what's the probability of flipping 2 tails only? How many times did that happen? 2 tails only. 1, 2, 3. 3. Do I see it anywhere else? Is there only 3? 3 out of 8. Perfect. So the probability of flipping 2 tails only was 3 out of 8. Okay, kind of interesting. Okay, so now let's do a tree diagram where we flip a coin and draw a marble. Here we go. Let's get to some more advanced ones, which they're really not bad because it's just you're showing all the possible outcomes. So here we go. What's the possible? So these are 2 independent events. If we flip a coin and draw something out of the hat, they will have no effect on each other, correct? So these are independent events. So what's the probability, so as a first event, flipping a coin, we can get a heads or tails. So we're going to get a heads or tails. Now we're going to go and draw out of a hat. Now we can draw out these different colors here. Notice orange has 2 oranges, correct? You see how we have 2 oranges, everybody? So we're making a tree diagram looking at possible outcomes. So here we go. So let's say we landed on the heads, and now we go over and draw out of the hat. What's my possible outcomes after I flipped my heads to draw out of the hat? We could get a blue, correct? We could then get a orange. We could get an orange, correct? We could get a red. We could get a green. Everybody see how I'm just making a tree diagram? Are those all the possibilities? Yep. Then tail for heads, that is. Let's pretend I drew out let's say I flipped a tails and then I go draw out of the hat. Let's say we got a tails. Well, that's good. Now moving on. We could get a blue. We could get a orange. We could get an orange. We could get a red. We could get a green marble. So now we listed out all the possible outcomes using a tree diagram. So we could get heads then blue, correct? We could get heads then orange. Heads then orange. We could get heads then red. Heads then green. These are the possible outcomes. So we could get a tails then blue. Tails then orange, tails then orange, tails then red. We could get a tails then green. So how many possible outcomes? 10. 10, correct? 10 possible outcomes. Now I want you to notice something about your tree diagram. If you just count the outside of your tree, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the possible outcome. So you can just use that. Okay. So what's the probability of getting a heads then an orange? How many times does that happen? 2 out of 10. 2 out of 10. That would be our answer. What is and we could write down the percentage as well, but I don't want to take the time to do that. What is the probability of getting a tails? How many tails are there? 5 out of 10. Well, does that make sense? Yeah. 50-50 chance we're going to get a tails, right? So do you see how using this, the probability makes sense? So 5 out of 10, which is 50%. That one we just know is pretty easy. All right, everybody understanding probability, okay? So really it's not too bad once you draw yourself a picture. Okay, so what I want you to do is I want you guys, so by yourselves, you can do it on your whiteboard or on your paper somewhere, I want you to make a tree diagram showing possible outcomes for flipping a coin twice and then drawing out of a bucket these marbles. And then I'm going to ask you some probabilities. So make yourself a tree diagram. I'm okay with you doing it on a whiteboard, but make sure you list out all your possible outcomes. You'll have 2 coins flip first. So heads, tails, heads, tails, heads, tails, right? And then go through and list these. And then list out your possible outcomes. Okay, ready, set, go. Okay, so now I'm going to ask you a question. This is some notation you want to probably get used to. This just means what's the probability you'll get 2 heads and a blue. So we know that there's a total of 20 possible outcomes. So now what's the probability, you got to read it very carefully, that you'll get 2 heads in a row, 2 heads, or just 2 heads in general, and then a blue. So how many times, look at your tree diagram, how many times does that happen? Look at your tree diagram, how many times out of 20 do we get 2 heads and a blue? 2 times. Very good, right? Does everybody see it? So we'd say 2 out of 20. Now I'm going to change the problem. What's the probability of getting a heads ever and a blue? So how many times does that happen? Look at your tree diagram and count. Look at your possible outcomes and think without writing them out. Let's see. I get 6. I get 6. So we have this possibility correct. We have heads, heads, then blue. And that happens twice, right? We get 1 head. Then we could get, oh yeah, heads, tails, then blue. And heads, tails, then blue. Again, correct? Then that's it for that part. Go on to tails. We could get tails, heads, then blue. Tails, heads, then blue, and that happens again. Heads, tails, then blue. Now there's no other heads besides that with the blue, correct? 1, 2, 3, 4, 5, 6 possible out of 20. Does everybody see how this is working? Not super hard, but not super easy either. You've got to be able to draw out a tree diagram, which is showing your possible ways of getting an answer. Okay, awesome. Okay, so now this is some more vocabulary here. So write this down. I wish I already had the notes typed out for you. The word sample space. Sample space is the possible outcomes, all possible outcomes. So there's a million different examples of what a sample space could be. It all depends on the problem. So for example, so write down the sample space means all possible outcomes. So for example, if I said to you, given that we have this class, what's the probability that there's a boy in it? The possible outcomes is all of us. So there would be 1, 2, we already said this, 1, 2, 3, 4, 5, 6 students. Does that make sense? So our possible outcomes would be the 6 students. Does everybody understand? Now let's change the problem. For example, let's say I was dealing with Westlake as a high school. I said, what's the probability that you're in Miss Christensen's class? Or well, that wasn't a very good example. Because then you would be dealing with teachers. You know what I mean? However many teachers divided by 1 of me. But like sample space could be many different things. The big picture. And then you'll see stuff written in set notation. So for example, let's pretend like the sample space is your name. So I want you to do this on a paper or something. So you'll say S, the sample space, and then they have these little brackets to list out what is in the sample space. So I'm going to make the sample space my personal full name, Whitney Christensen. You're going to do the same with your name. Now we always separate different things by commas. So W, H, I, T, mine's long, N, I'm going to have to push it, E, Y, Whitney, and then C, H, R, I, S, T, E, yeah, you guys get the picture. I'll let you guys do your name. And then I'm going to close my bracket. That's my sample space. That's an example of a sample space. My entire name. Okay, now, does everybody have their sample space written down? Now, a subset, if I said to you, what's a subset of the sample space? A subset is just a smaller piece of the sample space. So here's my sample space. If I take a subset of that, I'll just be taking a smaller piece of the sample space, just a part of it. So write that down. Subset means, if I said to you, find a subset, that just means take a smaller piece of the entire sample space. So these are just some examples. There's many different subsets in here. For example, an example of a subset would be putting your first name. So I'm going to call subset A So I'm naming a subset, just a different name. So this is my sample space S, so now I'm doing a subset, which is a smaller piece of the sample space. So I'm going to say A is my first name. That would be a smaller piece of the sample space, correct? So A is my first name, W-H, so you do the same thing, I-T-N-E-Y. I'm going to separate those by commas. There's an example of a subset. Does everybody understand what a subset is? Now there's a lot of different subsets. There's not a certain exact one. Let's say that I want a different subset. I'm going to call that subset B. Now let's make a different subset our last name, my last name, so Christensen. C-H-R-I-S-T-E-N-S-E-N. That's an example of a subset. My last name, just a smaller piece of the sample space. Now there's others, so you'll do the same thing. Make another subset, call it subset B, put your last name. Now just understand, it doesn't have to be anything in particular. Here's another example of the sample space, another subset. Let's call subset C. Now watch. I'm going to randomly pick H-C-H-R. H-C-H-R. That's still a smaller piece of the sample space. So do you see how subset just means a smaller piece of the sample space? Everybody understand? Okay. Awesome. Now union. The word union means, and you're going to see this notation. So write down this definition. Union. Union, you'll see by this sign, a U. That means united. The union, if you unite, you all come together, correct? So a union would be uniting subsets together. So if I said unite subset A and B, that would be putting my first name and last name back together. Does everybody understand? I'm uniting them back together. So it's taking two different subsets and unioning them. So you'll see it written like this. If I said A united with B, we're unioning them together. We're uniting. So we would put them back together. Whitney Christensen. Put them back together. That would be a union. Everybody understand? Okay? Now an intersection. Intersection is where they are the same. So if you intersect, that's where you cross over, correct everybody? You intersect and then you cross. So an intersection is a crossing. So an intersection is going to have this symbol, this upside down frown, I call it. So here's how I like to, here's a little trick that helps me remember which one's the intersection, which one's the union. So look at this. It looks like a smiley face. When everyone's united, we're all happy. We all are welcome in the group, correct? Now this is an intersection and it's a frown. Not everybody's welcome. You only let people that are the exact same as you come in. Does that make sense, everybody? So if I look at this subset and this subset, you're only allowing things that are the exact same come into the intersection. So the intersection of A and B would be where they're the same. So let's look at my first name, for example, and last name and see where they intersect. We have a W here. Is there a W there? Well, they're not the same, so they're not welcome. Picky people don't let other people into their friend group unless they're the exact same as them. Does that make sense, everybody? So H, is there an H? First name H, is there an H over here? Okay, then it gets to come because it's intersecting. They're the exact same. Does everybody understand? So an intersection, H would get a come. I, and my name, yep, I gets to come because they're the exact same. T, he, and Christensen, yes, so they get to come. You guys get the picture here. And that's the only people welcome is the intersection, where they're the same. Pretty easy, right? As long as you know the notation. And then complement means everything not in the subset. So write down that word, complement. Have you guys been writing down these definitions, intersection, union, and then the symbols for them? Okay. Complement will be written as I'm going to scroll up so you can see. So complement is everything that's not in the subset. You're going to see it written like this. A with a little c up there. B with a little c. So complement is everything not in the subset. So A was my first name. W-H-I-T-N-E-Y. And then the sample space was Whitney Christensen. I'm just doing it messy, so I don't have to write it perfect. Okay, I'm just giving you some room to see. Okay, so if I said to you a complement, that means everything that's not in this sample space. It means everything that's not in that's in this sample space. Everything that's not in the subset. So W, it's everything that's not in that. So W is in that. Does that make sense? H-I-T-N-E-Y. So everything that's not in that would be a complement. So it would be Christensen. Does that make sense, everybody? Everything that's not in subset A. Okay, here we go practicing that. Okay, so I would go to another page, maybe the second page, and start taking some notes there. So here's some examples. So write this down. Given the sample space S is equal to 0, 1, 2, 3, 4, 5, and given a smaller subset A, a smaller piece of the sample space is A, and event B is another subset, a different subset of the sample space, we're going to go through and answer these questions. So we all understand that this is the sample space, so this is all of the possibilities. Here's a subset, a smaller possibility from that. We pulled it over here. We put it back, and we made a new subset, so we pulled down this. They have nothing to do with each other. Does that make sense? Everybody, they're just different subsets of the sample space. So let's find A union B. So remember, united is everybody's welcome, the union of both. So that would be combining this and this. Does everybody understand? So let's put in our parentheses here. So 3, 4, 5, 6. That's all going to be there. 3, 4, 5, 6 is all going to be there. Now, also in this, we have 1, 2. It gets to come. 1 and 2, we're uniting them. Haven't we already listed out 3? We've already listed 3. Now look in the sample space. There wasn't more than 1 3, so we're not going to list 3 twice. Does everybody see? I'd be double dipping. 3 is already there, and then 4 is already there. So there would be them united. Now let's do A intersect B. Now it's the picky people, only where they're the exact same do they get to come into our subset. So where do they intersect? If this has a 3, is it the same as this? Does this one have a 3 too? Yep, so 3 gets to come. 4, 4, yep, 4 gets to come. And then 5, 5, no. 6, 6, no. So that's it, correct? That's the only places they intersect. That's the only people that are the same. A complement means everything that's not in A. That has nothing to do with B. Look at the sample space. Everything that's not in A. A complement. So what's not in A? Well, A has a 3, a 4, a 5, and, oh, I said 6. So 6 must have been intended to be up here in my sample space. Sorry about that. Okay. All right. So everything that is not, back to everything that is not in A. So wouldn't that be 0, 1, and 2? We're all understanding set notation. 0, 1, and 2. Now these aren't probabilities. These are just getting in some vocabulary and understanding what complement means, right? Like you guys understand that this isn't probability, right? We're looking at possible outcomes and stuff. Okay. Awesome. So you guys do that one. So, an example like the worksheet. This is going to be like your homework, so we're almost there. But this part is probably one of the easier parts. So first of all, what we're going to do is I'm going to show you how this is called like a probability area model. It's just a way to list out totals and whatnot and then use it to find probabilities. So I want to ask the class, how many males do we have in the class? We're going to include me in this, okay? How many males do we have in the class now that Logan's gone? How many males do we have? 1. Okay, so we have 1 male. So notice he's a male. If you had to choose, even if you don't have a preference, you have to choose. Would you choose BYU or U of U? U of U. Okay. So we have a male that chooses U of U. 1 male. So there's 0 males that choose BYU, right? And so how many total males? 1. Does everybody see how this is working? All right. Interesting. Now how many females do we have? 1, 2, 3, 4, 5. Okay. So there's 5 females. Right here will be 5. How many of you would choose BYU? 0. Okay, so then I'm going to choose it just to be different. 1. And so that means 1, 2, 3, 4 of you choose the U. Okay? Now that all adds up, right? 5 and 5. Okay, so now let's add up how many people like BYU total. 0 plus 1, correct? 1 female and 0 males like BYU. Does everybody see that this is the total for BYU people? That's the hardest part, is people get them messed up in their head. 1 person in the room chose BYU. And then U of U, how many people chose U of U? 5. So once again, how many total people do we have? 6. So right down here, this corner will be the grand total. Does everybody see how this is working? So now we can go through and find these probabilities. Are you ready? So this is all your homework is. So watch. Find the probability of girls. So how many girls and how many females? 1 plus 4. So can we just look right here? 5 out of 6. Let's write it as a fraction. On your homework, you'll do both fraction and percent, but we won't keep doing that. What's the probability that someone likes the U of U over BYU? How many people chose U of U? 5 out of 6. So do you see how this makes it really easy to do probabilities? What's the probability? Now we got to be careful because there's unions and intersections. What's the probability of boys united with BYU people? So now isn't both welcome? Everybody's, this is a friendly one, right? United. So how many boys total? How many boys? Negative comes. How many boys do we have? 1. Now we're uniting it with how many BYU fans? Let's look at the BYU fans. Now, haven't we already accounted for that one? There's only one other BYU fan, correct? So 1 and 1 would be how many people? 2 out of 6. Does everybody see? All right, now let's do this one. And let's do this one. Let's go to the easier ones without a complement first. Girls intersect, and I'm going to erase those red check marks. This always really helps, so I don't double dip on accident, and you'll see what I mean. Now we're doing girls intersect BYU. So now that's the picky one, is where they intersect and only where they intersect. Does that make sense, everybody? So find girls, females, that intersect BYU. You see where this is the only place that they intersect. So 1 out of 6. Boys intersect. Okay, let's do actually this one now. I'm going to erase that check mark, starting over. Let's do this one. BYU complement. So what does that mean? What does BYU complement mean? Isn't that liking to you? Or everything that doesn't like BYU is what it's really saying, right? So let's go check off the ones that do like BYU. So these are the ones that chose BYU, correct? So how many did not choose BYU? Those 2, correct? Does everybody see how you're not gonna, you could look at it a few different ways, but if you look in here, it kind of makes it easy so you don't get confused. 1 person plus 4 people, it was 5 out of 6. Was BYU complement. Okay. So let's do U of U complement. So won't that be, so U of U complement means everybody that doesn't choose U of U. So these people chose U of U. So how many did not choose U of U? 1 plus 0, which is 1 out of 6. Okay, we're almost there. Sorry, erasing this, because this next part's probably the harder part. Okay, so here, let's look at this one. Girls united with BYU complement. So you ever say to yourself, what does that mean? So I'm looking at it in sections. Now notice the complement's not all of it, correct? It says BYU complement. So girls united with BYU complement is U, correct? The U. If you don't like BYU, you like the U. So I'm going to change BYU complement to the U. So girls united with U fans. So girls get to come, females get to come. It's united, so everybody gets to come. United with the U fans. So here's the U fans. Now you won't count for that 4 again. We've already counted for those 4 people. Do you see what I'm saying? You can't count for those twice. So now how many people? 4, 5, 6 out of 6. So that union was 100% likely to happen if we united them. Does everybody understand? Okay. Okay, so go to your worksheet and go to, is this, oh no, I don't think this one is on the worksheet, is it? Do you need more examples of that, or do you feel pretty good about it? Because I won't keep going if you feel good. Do you want one more? Are you good? You guys are good? Okay. Then do problems 1 through 10 and 11 through 14 on the worksheet, and then check with me. Looking up here, find the probability of the following. So these are just totals, correct? So these are the total yeses. These are the total no's. So here's Pierce. Everybody good? This is the total females. This is the total males. Does everybody understand? Okay, this is our grand total. So our probability should always be out of that. Okay, so it says, what's the probability that a person has their ears pierced? Find the ears pierced. It's not the yeses. Check them off. How many of that? 103 out of 178. Now let's do, I'm going to erase it because I like to have a fresh slate every time. What is the probability? It's a male with pierced ears. So that's the intersection. It has to be a male with pierced ears. So it has to be male, and they have to be pierced ears. How many of that? There's only 19 of them, correct? 19 out of 178. Okay, let's keep going. Male or has ears pierced. So isn't this a friendly one? They're either male or they have their ears pierced. So let's go check out the first one. Male. Male is ding ding. That's male, correct? Isn't that in the male one? Or has their ears pierced. So that's the yeses. We've already checked out that, yes? So now add up 19 plus 84 plus 71. 174 out of 178. Does everybody see how to do the union? I checked them off. The ones that were united and got to come. Okay, I'm starting from fresh. So it says, what is it? The probability that they're female. Check, check, right? So 88. What's the probability? A female with pierced ears. So they have to be both. They have to be female and they have to have pierced ears. So that'd be 84. Female or has pierced ears. So if they're female, they get a come. Ding, ding. Or they have pierced ears. That's in the yes. We've already checked out that. So now you'll add those up. 19 plus 84 plus 4. Does everybody see how to do that? Okay. Is it the complements that are throwing you off or what's throwing you off? Okay, let's do, is a female union, okay, I'm going to do this. Probability that it's a female united with ears pierced complement. So I look at ears pierced complement would be not ears pierced, correct? So just rewrite the problem. This is the probability that a female is united with no ears pierced. That's the same thing. Does everybody see how to rewrite it? So that kind of looks so fun. That's fun. Anyways, female united with no ears pierced. Union means everybody gets to come. So go to female. Check, check. United with no. We've already checked that. No. Check that. No. Add them up. Do you see how that works? Does that help a little bit? Think you're good now? Keep going. Try, go back again and try again. Okay.